On today's video, we're going to be talking about radical halogenation. Some things to consider for this mechanism is that radicals are highly unstable. The formation of a radical requires energy in the form of either sunlight, UV light, or heat energy. And the weakest bond breaks when a radical is formed. And we'll all get to that in the mechanisms next. Step 1 of radical halogenation involves the formation of a radical. This process happens by putting energy in with a molecule such as Br2. So putting in UV light, as shown here, actually breaks that bond in between the two bromine atoms, leaving two bromines with only one electron on each that is unpaired, which is the formation of a radical. So that is the initiation step of halogenation by a radical. So now we go to step 2, which is propagation of the radicals. So in the presence of methane, a free radical bromide will actually donate its one electron and break a bond between a C and an H in methane. And what happens is this bond breaks, and the two electrons join together and form HBr and leave the methane that did have 4 hydrogens on it with only 3 and then a radical electron there that's unpaired. And then the reaction goes further on, as you see here, where the free radical methane donates its free electron to another Br2 molecule, which actually breaks the bond between two bromines. And then we have our product here formed, the bromomethane, and then another bromine free radical. And that step is actually called termination, where you actually have a product with no radicals present. So here's the 3 products that you can get from the whole mechanism. And the first 2 methane free radicals that come together, that's called radical coupling, where you have a radical formed between 2 separate molecules, and then they just come back together. So in the presence of ethane, if we had heat or light put into the reaction, it would also go in the backwards direction and form those methane radicals. And the same goes with the Br2 and even with the bromomethane here. So some contributing factors to this radical halogenation reaction involves the stability of the formed radical. So the difference in between, say, a secondary and just a methyl radical. Methyl radical is going to be much less stable than something that has more electron density around it. And just the same thing we've been learning through organic, that it goes primary, secondary, tertiary when it comes to stability. It's the same with radicals. Alkenes and alkynes actually do a radical addition mechanism that we'll talk about later in this video. And the regio and stereoselectivity is actually different between halogens such as Br2 and Cl2. Actually, the bromine is much more selective than the chlorine compared to its radical halogenation. Now we're going to get a little more complex with this radical addition mechanism. Actually, it's the same mechanism. It's all very easy and simple compared to a lot of the organic chemistry we've done so far. We're just going to be using a different reagent for this mechanism here. So hopefully we can start by getting the pen to work. All right, got a new pen. So we're going to be using NBS as our reagent for this. And it has a nitrogen bonded to a bromine, like so. And this is actually a very weak bond, so let's remember that for this mechanism. So the first step is homolysis of this bond here. So this bond's going to break. And we're going to be left with this nitrogen reagent here that has a free radical, and as well a bromine atom with a free radical. And we're going to add in such as something like methane or ethane, something with really anything that has a hydrogen on it that can be taken off. So we're going to just call that R with a hydrogen. And this is our substitution step. So we're going to put SN2 there. So we have our free radical adding there, and then that bond's going to break over here, adding the hydrogen to our bromine radical, leaving this R group with its own radical. So let's go down here and show that. And then R radical, just like that. So for the last step, well, second to last step, before our product is formed, we actually have this acidic combination of the leftover NBS that hasn't been used. So we're gonna put that in there. So both of these oxygen atoms are still playing a role. And they're actually going to act as an acid by taking this hydrogen away from that bromine. So let's draw that. And it's still going to be 2 electrons here. So let's make sure we have that arrow with the double head on it. So now we have bromine with a negative charge. And then we also have bromine still bonded to that NBS. And a positively charged O there. And this negatively charged bromine is actually going to be a nucleophile in this, where it's going to donate its electrons to this bromine, and this bond's going to break right here and then go all the way up to the oxygen. So I'm going to show that step. So we still have our 2 bromines. And we have this NBS molecule that doesn't have the bromine on it anymore. That is also able to tautomerize into, I'll just show the tautomerization here. With that nitrogen and the oxygen molecule. So this is separate here, and we have tautomerization between that hydrogen to this nitrogen. And then our product that's formed is this Br2 right here. That was our wanted product through radical halogenation of NBS. So for the last mechanism, I'm going to be drawing the radical halogenation between an alkene or an alkyne and then a halogen radical. And this is actually called radical addition. So here we go.